We've dealt with bolus dose kinetics so far. Now we'll get into drug infusions. As usual, we'll start simple with the one compartment model, deal with steady state conditions, and the other factors that are listed on this slide. Zero order infusions are very important in pharmacokinetics. It's a very frequent method of administering drugs and source of PK data. The steady state condition is important to appreciate. Input divided by loss. Drug absorption is frequently zero order, and constant rate input is a key phenomenon in pharmacodynamics. Here's an example of a drug, actually a protein that was given by constant rate infusion. You see the concentrations versus time. You see the plasma concentrations rising up to what appears to be a steady state. The infusion stops at 75 minutes, and there's washout of the drug. So this is a typical profile. What can we learn about it? So we want to know how high it goes, the concentration at steady state. How fast it rises, what determines that? And what determines the washout kinetics? So we'll deal with the basic one compartment model for drug infusion. The parameters are defined on the slide. I try to be consistent with what we always use as symbols for various pharmacokinetic models, and they are listed on the slide. What's special about zero order infusion is time, where capital T will represent the duration of the input. So with our basic one compartment model, the differential equation for this is V times dCBT equals K0 minus clearance times plasma concentration. Initial condition, in this case, is 0. So this is the naturalistic function. Concentrations are what we're going to look at and model. And we'll find out that one explicit solution for this is the equation at the bottom, where plasma concentrations will be K0 over clearance, and then that 1 minus exponential. But that applies to only certain conditions of infusions. So the Laplace derivation of this model is shown on the slide. In this course, I won't expect you to do complicated Laplace derivations, but as usual, I want people to understand where the equations come from, and when you see derivations, you can know that they have a nice mathematical basis. So this derivation has a special Laplace transform for a constant, K0. So the constant is basically the constant divided by S. And then the disposition part of it is the one we've seen before for a mono-exponential. And this directly gives us the anti-transform at the bottom of the slide. So let's look at the first behavior of this function. So it basically says that plasma concentrations will rise, and if they continue, they'll reach a steady state. So what we see in the equation is that in the exponential, as time approaches infinity, e to the minus kt approaches 0. So the plasma concentration at steady state then is what's left in the equation, K0 over clearance. And this is a very important relationship because we'll employ the bottom equation, clearance equals infusion rate by steady state concentration, as a model independent parameter. How long does it take to reach steady state? Well, the rule of thumb is about 4 half-lives or more. So we can find a derivation for what's going on here if we look at the details on the slide. So suppose we consider what happens at time equal to 1 half-life of the drug. Remember, half-life is 0.693 over KEL. KEL is clearance over volume. So we can plug in the half-life. We can determine the plasma concentration at the half-life of an approach to see steady state. And we come up with this exponential term of 0.5. So in the bottom, what we see is that plasma concentration at one half-life will be 1/2 of the steady state concentration. So the up curves, as derived here, are controlled by half-life, actually by the clearance and volume. And of course, half-life will determine the washout part that we will get to. So we can look at the rate of approach to steady state. So this is a nice empirical calculation. So at one half-life, we're at 0.5 of steady state. At two half-lives, we'll be at 0.75. At three half-lives, 0.88, 4, and then 5. So actually at five half-lives, we're at 0.97 times the steady state. So this is why we say it takes at least 4 half-lives to reach steady state. Because what is steady state? If we're at better than 0.9, we're pretty close. So this is the kind of the rule of thumb that I talked about. 4 half-lives is often important. One interesting thing about this infusion equation is that we can reverse it. So if we take the top equation, factor out CPSS, move CPSS to the left-hand side, subtraction, we're left with CPS with the exponential. We can take the natural or base 10 logs of each side, and what we expect to happen is what I show on the graph. So if we plot CPSS versus CP on a log scale, in this case, we'll see the down curve with the slope being the K value. So if we only have up curve data, this is a useful approach of trying to identify the KEL value and the half-life of the drug. So we see this summary of the basic properties of infusions, the exponential rise, the steady state condition. Also see that K0 is equal to clearance times CPSS, or turning it around, clearance equals K0 over CPSS. And the time course, the half-lives that we talked about. Oftentimes in clinical therapy, if we know we're giving an infusion of the drug, patients may need a loading dose of the drug. So a simple derivation for the one compartment model to get the loading dose is that if we know the CPSS, maybe we want to target a CP0 that's the same. So ZP0 would be that DL, loading dose, divided by volume of distribution. So if we have volume of distribution, we can calculate a CP0 value. And then what we'd expect if we give a bolus dose along with the zero order infusion is that we can add up the two curves on the left and we get the curve on the right. We get perfect steady state right from time 0. So this works nicely for a one compartment model. It'll get more complicated for more complex situations. Oh, here's the more detailed calculations of the loading dose. This basically gives you the derivation that we would end up with. When we give infusions, we often have washout of the drug. So that's what I showed for TPA. So let's see what happens with our equations before and after cap T. So in this case, we have the differential equation after time. means that we're only going to have clearance of the drug. So we have the exponential washout phase. And then the starting point at this situation, the initial condition, is what we call CP prime or the CP steady state if it reached steady state. So we can plug in those equations from the right, the CP capital T, and we can solve for plasma concentrations after time t. So that's the bottom equation. What happens after time t? Then we have Cp prime times the exponential k times the time elapsed, or it's the steady state with the exponential. Time is time elapsed. So in a way, this is a mathematical proof that the washout will be mono-exponential. A very common situation is a short-term infusion. So the graph shows what would happen there. So we have plasma concentrations rising up to the T, capital T. We hit the CP prime, and then we have the washout. So what the derivation involves is identifying the CP prime at the capital T. And then we have the washout. We can make a substitution we see partway down the slide. And then we end up with the equation at the bottom. So this equation is really neat. It's a very key equation. And we'll see a similar equation for more complicated kinetic models. So what do we see? At the bottom, we have a complete equation for the entire curve. So we basically have part of the equation describing the joint effect of the infusion plus drug being cleared during that time. And then we have the exponential washout. But this equation is special. It cannot operate directly as it is viewed. We have to put an if statement in or a where statement. So this is where we have to control the operation of the equation. So when we're operating this equation, we have to put in the conditions that capital T is going to be equal to the actual time when the time is less than cap T. And then at and after cap T, T becomes equal or greater than capital T. So we basically have a changing value of what the cap T is in the equation. So that makes it tricky in operating computer programs and then coding for computer programs. We have to have this mathematical proviso in recognizing the operation of the equation. So what further happens then with a short-term infusion is when we look at data, we see that there's a change in the intercept. So that's pictured on the graph. If we had an IV bolus dose of the drug, we'd have the simple mono-exponential in this case. So if we have a short-term infusion, we see the curve rising up to cap T at Cmax and then declining. So what happens here then, we recognize that the terminal slope is the same. It's shown and can be proven mathematically. But C cap I is the intercept. So what is the intercept in this case? It's pictured as a broken line. And the cap intercept is that exponential term that you see at the top. So that relates to just the up curve of the data, and it says that what it does, that that intercept is going to be a larger value than the bolus dose intercept. Why is it larger? Well, visualizing, we see that input of the drug is slow. It's delayed before the full dose is in. So that's creating the visual condition that we see. So what further happens then, if we want to handle the pharmacokinetics, we often want to use the intercept value. And what's sometimes done in pharmacokinetics is that when we have a short-term infusion, we have an intercept, and because we know about bolus dose equations, we might want to convert the infusion intercept to what the bolus intercept would have been. So there's a brief derivation there, and we get to the equation at the bottom right. So if we want to know the bolus dose CP0, we then have the CI in there. We put in the cap T. We have to know the rate constant, the exponential term on the bottom. So this is a way of converting then. Basically, it's adjusting and recognizing that what happens to infusion intercepts and also slopes. I've talked in terms of infusions of drug, and that's what one might recognize as the most common situation in pharmacokinetics, because infusions are commonly given. It may not be safe to give a bolus dose. So we may have PK data that is according to a short-term infusion. We may or may not have the up curve in the data. But I bring to your attention that zero-order input is commonplace in drug absorption as well. So here's some data where an ACE inhibitor, enalapril, was given, and the plasma concentrations of its active metabolite are shown as the black dots. So that's a semi-log plot for the plasma concentrations. There's also PD data on this slide, the ACE activity, the inhibition of the enzyme activity. And what was done here is application of our general equation that we have at the bottom. So basically, when we have drug absorption, we can operate this equation, but we need those provisional time values in one instance. But what was done here is that the data were actually fitted, where the fitted parameters are listed on the slide. So in this case, the duration of input was not truly known. It was fitted to be 3.2 hours. K0 was dose, or might be F dose over tau. So the zero order input for drug absorption is the dose divided by the duration of absorption. And then the data would yield the clearance and the volume of distribution, because we have clearance in the equation and the K value gives us the volume term. But we also can fit these data using the differential equation. Actually, it's easier. So if we go back to the zero order differential equation for one compartment model, we have dCp dt equal K0 minus clearance times Cp all divided by F. So here the same fitting can be done. And then what is done here is that K0 is once again dose over cap T. And here what's done is that K0 has an input when time is less than cap T. And then K0 goes to 0 when time is greater than cap T. So this is commonplace for drug absorption. These kinds of equations need special coding, or the software must build it in. So where I say where, it's like an if-then statement. If k0 equals 0, then t less than t, really the reverse. When t greater than t, then k0 equals 0. So basically, there's a couple of ways of operating constant rate input equations for drug absorption, but it will get a little more complicated with there's a bioavailability factor that might be obvious. Oh, here's the kind of simple calculations that a clinical pharmacist might do. So they're giving an antibiotic, half-life of 8 hours. Volume is often some proportion of body weight. And if we use a one compartment model, we'll know that if we start infusing this drug, it's going to reach steady state in roughly 32 or more hours. We can calculate what the concentration will be if we know the infusion rate. So if it's 45 milligrams per hour, given for, say, 3 days, that will be steady state. We can use our steady state equation at the bottom, K0 over clearance, and we'll end up with 43.3 milligrams per liter as the concentration. The pharmacists often want to give a loading dose, especially for antibiotics. The patient is sick. He needs the drug right away. What's our loading dose? Well, we know the target CPSS. We're given the volume, so we can calculate the loading dose, and that's pretty simple. And then we might want to know what happens during the washout. So we know the washout will be the mono-exponential kinetics. So the washout will start with the steady state concentrations. We have the K value from clearance over volume, and we can then calculate from the exponential what the concentration might be, let's say, at 24 hours later. Again, this is the basis for lots of calculations that pharmacists do. So what we see for this is that infusions are a frequent mode of drug therapy and source of PK data. We got to know how to deal with them. The rise and rate of washout are governed by K for a one compartment model. The steady state is an important condition. It's K0 divided by clearance. It's one of the reasons clearance is so very important is because it determines steady state concentrations. Resolving PK parameters gets more complicated. We can convert intercepts to bolus intercepts, or we can operate differential equations, or we can operate explicit equations, but those equations need the special attention of adjusting them for when time is before the stop of the infusion versus when time is after the infusion ends. So it gets a little bit complicated.